Okay, imagine standing on top of a straight up ladder that suddenly starts sliding sideways on a slippery floor. So here is the ladder, and here is the girl Alice. And her mass, M, is small compared to my ladder, which has capital M as mass. And the question is, during the fall, the ladder is sliding on a frictionless floor here. Will Alice ever lose contact with the top of the ladder? That's the question, and free fall herself. So let's investigate this. And if that is the case, what angle theta would it be when Alice loses contact? So just use the laws of physics, and the center of mass of the ladder is here. And as the total length of the ladder is 2L, this length here to the center of mass is just L. And the first thing we see, the center of mass law is saying the sum of the forces equal the mass of the body times the acceleration of the center of mass. But as you see, there are no forces in the x direction here. Here is x and here is y. So what we get is simply the sum of the forces are 0 in the x direction, and it still must be equal this. But if the acceleration is 0, yeah, then the velocity must be a constant, right? And from the initial condition, we start with the ladder straight up and no velocity whatsoever in the x or y direction. So then the velocity here in the x direction is 0. And if that is 0, yeah, then the position of the center of mass must be a constant, right? And if we say that this, x equals 0 here, well, it's not really consistent with this coordinate system, but it doesn't really matter. Let's just say xg here is a constant, and remove that 0 here. Then it's consistent with the coordinate system here. So the interesting thing is that the center of mass will never move in the x direction because it is a constant for all times. So the center of mass will move downwards here. And of course, the ladder here will slide here and also rotate about the center of mass. So just from that little equation there, we already figured out a lot in this problem. And let's also look at the forces in the y direction. And you have one in the positive y direction, in the same direction as the y direction, and you have a negative force in the y direction, the gravitational force. So it's just this minus this, and that should be the mass times the acceleration of the center of mass in the y direction. So this is telling us something about what is going to happen when the center of mass is accelerating downwards here. And another thing, the acceleration of the top, where Alice is standing, how much is that point here actually accelerating? That is the question, isn't it? And first of all, the y value of the center of mass is obviously L sine theta. Here is the angle theta. And of course, this y value here, that must be 2L sine theta. So what it means is that the acceleration here is one thing, and here it is twice that in the y direction. So we're introducing the condition that there is a loss of contact here if that point of the ladder is accelerating downwards with minus g. And Alice will fall also with minus g, but there is no longer any contact force here. So we introduce that here. If the acceleration at the top of the ladder, that y value is minus g, and this must be twice the acceleration of the center of mass in the y direction. So one condition for this, you can say the y acceleration of the center of mass is minus g half. It comes from that. And then we can use equation 2 here and figure out the force. Very easy, really. So Fy equal mg plus this, but that's negative. So what you get is this force is mg over 2 in that exact instant when Alice would lose contact with the top here. So that force is mg divided by 2 in that case. And then let's take a look also at the torque with respect to the center of mass in the z direction. So what kind of torque do we have? So here, all right, the gravitational force doesn't introduce any torque in that exact point. So the only thing is that force here. And then you can move, for your vector product, you can move the force up here. So then the moment arm is like this, times the Fy. And what is that distance? It's the same as that distance here, right? And what is that? If that is L, then this distance is certainly L cos theta, right? So you have L cos theta Fy. And that should be something like the moment of inertia times angular acceleration. But in this case, we are using the angle theta. And you can see during the fall, theta will decrease, not increase. And so that means if theta is negative, then also theta dot and theta dot dot is negative. So we introduced the sign correctly here immediately. This first, the torque here is in the z direction, and you can see it's positive. L cos theta is positive. Fy, that was a force in the positive y direction, so that's positive. And the moment of inertia is positive. So, and we know theta dot dot is negative. So there must be a minus sign here to make this positive in agreement with the sign of this left side here, which is also positive. So this is the equation. It must be that torque equation. Okay, and then we can introduce the force in y direction, mg over half. And we can introduce the moment of inertia for a ladder with length 2L. I'm just giving it here. And from this, we can now solve cos theta. And it turns out to be this. And now we could calculate theta if we knew the theta dot dot. So that is the question. What is theta dot dot? And we can try to figure this out. So if we go up to the figure again, the y value of the center of mass, here is the center of mass, this is distance L, so the y value is that distance here. Obviously that is L sine theta, right? That's what I write here. And then we can figure out what is the velocity of the center of mass. Then we differentiate with respect to time. We get this. Here we get the acceleration. And this part here we already know. Because I That's the condition when Alice is losing contact. So that we know. So that's minus g half here. So then you can say, okay, so that can be written like that. And then we introduce the equation 4. If we multiply with cosine theta here, we get cos squared theta equal this, and cos theta, of course. So this is exactly what you have here. And the L theta dot cos theta, that is given here in this equation 5. So we can introduce that and get rid of the problem with theta dot. So now, as you see here, equal this. And now you have something theta dot squared instead, which is simpler than theta dot. And this is equivalent to this. So now the question is, what is theta dot squared? The angular velocity squared. And we can use that energy is conserved because there is no friction and the forces are conservative, the gravitational force. And the mechanical energy for a body is this kinetic energy. That's the kinetic rotation energy around the center of mass. And here is, if the center of mass has a certain speed, then you have also translational energy, kinetic energy. And here is the potential energy in the gravitational field. So mg, and then the height above ground and to the center of mass. So that's the yg value, right? And now we can say, what is the energy from the start? Then, yeah, the ladder is straight up, so the height is L, mg, and there is no kinetic energy. We started from rest with the ladder, so it's just mgl. And then at a later point, there is a rotation here around the center of mass. There is a translational kinetic energy of the center of mass, and obviously the potential gravitational energy here. So we can figure out this velocity since y dot equal this, and in the beginning of the problem I said xg is a constant. Yeah, okay, then xg dot must be 0. So really the velocity of the center of mass is just this yg squared. So let's do that, and that's what's happening here. So then you get mgl, and then j, we already said above, ml squared over 3 times 1/2, so it's this with the 6, theta dot squared, and then introduce that translational kinetic energy from here, and it is this term, and then mgyg. Yeah, what is yg? That is L sine theta. So, and then you start simplifying, move over this to that side, then you get this one, and then theta dot squared, and this, and you can now calculate theta dot squared. It's this thing here. So, for example, if you can use this in equation 6. And what is equation 6? Yeah, it was this one. So here everything is about theta and equals something that we know, L and G. And we wanted to know theta dot squared too. And this is exactly what we just found, theta dot squared. So we put in all that information here, and you get this. And then, unfortunately, there is no simple solution to this equation here. But what you have here is equivalent to what you see here. And if you want, you can plot one function. Let's call this y1, and here is another function, y2. And then you plot that in Matlab for different theta values. And then you ask the question, when is the function y1 equal y2? And what you will find is that theta equals 67.9 degrees. That is, in fact, when the acceleration of the top of the ladder is minus g. And that's exactly the moment when Alice will lose contact with that top of the ladder. So I actually made a full calculation here where we actually can derive the acceleration of the top of the ladder for any angle. And you see here, for example, the acceleration divided by g, when that is minus 1, then this is of course minus g. So here you can again in this curve see that is 67.9 degrees. You can read that here. Boom. Minus 1, 67 here. And you can get it for any angle here. You can find out the acceleration on the top of the ladder. For example, at the start, when the ladder is straight up, then it turns out that the acceleration downwards of the top is 0. I think we can realize that that is correct. And then as the ladder angle is changing, we get different accelerations. And here you have the value exactly when the ladder is hitting the floor. So it's a horizontal orientation. And then you see that then the acceleration of the left part of the ladder is 0 here and minus 1.5 g. So that actually that point is accelerating faster than g. So that's interesting. And this is also why it goes so fast, that point, so anyone standing will eventually lose contact with the ladder. Okay.